Okay, so I'd like to welcome you all here. It's about 4 after, so let's get started. So I'd like to first welcome everybody here. This is an expansion of our Getting Started series. We're getting started with Habana. We've had several webinars. Really, we've run them over the last 12 months. Really, how about getting started using Habana Gaudi for training? And now we're expanding this into how we use Gaudi for use with large models, especially focused on DeepSpeed optimization. So my name is Greg Soraki. I'm part of the applications engineering team. So we have Leon Tran also here from the applications engineering team who'll be supporting and answering questions. And Ken Levkovich from our product team also here to support questions and things coming in from the panel. For those of you, as we go through the presentation, please use the Zoom question and answer window. So you can go ahead and type your questions real time, and Ken or Leon will answer them. And then we'll have time at the end to do some Q&A as well. So please feel free to just start putting your questions in the Q&A. Okay, so we're this is being recorded and will be made available for later viewing from our developer website. And again, please use the question and answer tab, and we'll do Q&A at the end. So why are we here? Our objective in this next hour is to make sure that you as users are familiar with DeepSpeed and how it works on Habana. We'll talk about what DeepSpeed is and the steps needed to enable it on Gaudi and Gaudi 2, which is basically the same. DeepSpeed does some really interesting things to manage memory. And so those optimizer techniques are called ZeRO, so ZeRO1 and ZeRO2. And activation checkpointing will show how those are used to reduce memory on a large model. And we'll also show you some of the APIs that we have in our Synapse AI software stack that you can use to detect the peak memory or memory consumption of any model. And then we'll have wrap up and questions. So we really want you as a user today to walk away going, yeah, I see, here's some resources on where I can run models. Here's the details of how to do it. And so that you can start running these on your own. So let's take a step back for a moment and talk about Gaudi. So if you've attended some of our previous webinars, or you can go to our developer website and see the previous webinars, we talk about Gaudi. So let's just take a moment though, for those that are not familiar, what is Gaudi? Gaudi is our AI training processor. We remember this is a chip, a system designed from the ground up for AI training. This is not a GPU. This is a dedicated ASIC specifically designed to do AI training and inference. So we remember that the architecture of this has an optimized matrix multiplication engine and 8 tensor processing cores that are fully optimized for running deep learning workloads. It has 32 gigabytes of on-package high bandwidth memory to hold models and make sure we're managing these large models. And again, we remember one of the key differentiators about Gaudi is the integrated 10 100 gigabit Ethernet ports. So on an instance like DL1 in AWS, or in a chassis like Supermicro that has 8 Gaudis, all 8 of those Gaudis are fully interconnected over those 100 gigabit Ethernet on-die ports. So this really drives efficiency and scalability when we're looking at workloads across 8 cards and even supporting multi-node going out of the box and looking at 16, 32, 128 cards. A key differentiator. So when we look at training today, we look at some really key use cases, both existing and emerging. So today we know computer vision and natural language processing are really some core fundamental use cases. And today we'll obviously talk about these large models that are a key part of natural language processing. We also look at multimodal. In this case, where we look at today, stable diffusion is an example of this, where we have a text input and a visual output. We have question and answering, where you could take a video or a picture and ask this ask a question of the picture and get responses back. So we're seeing this emergence of all these use cases where text and video and imaging and question and answering and translation are all coming together and working together. So to drive the need for improved accuracy and performance, we see today these models getting larger and larger and larger. So we're on a path to 1 trillion. We're already there, and in some cases you could argue we're even past that now when you look at what's in papers and models coming out of the industry and academia. So if we take a look at a little bit of history, we see GPT and we see BERT that really kicked off the industry, and now we've just almost gone exponential. Looking at Megatron, Turing NLG, GPT-3 or /Bloom, we're at an exponential pace to go well past 1 trillion parameters in these extremely large models that drive, as we want, state-of-the-art accuracy and performance. So the issue here is current hardware solutions and current software solutions can't hold these models. It becomes very, very difficult to manage them. And advanced techniques are now required to do it. And we look at even what we've been doing over the last few years, talking about just basic data parallelism, where we take the data set and split the data set across models. Or we now look at model parallelism, where the model, like in these cases, the model's so big, we'll take the model and split the model across multiple compute nodes. Even those have limitations now. So we have to look at even more advanced techniques and more ways to optimize how to manage the memory of the model and the training, as well as the model itself. And we talk about one way to do that is using a library called DeepSpeed. And so let's talk about DeepSpeed and how that really has evolved to become a significant advancement on how we can manage these very, very large models. So what is DeepSpeed? Many of you have heard of this. You know, we look at the kickoff poll here. 29% of you say that your organization uses multi-node and some parallelism. But for this audience today, you know, 71% of you say that working with large models is still an emerging skill. So let's talk about what DeepSpeed really is. DeepSpeed is produced by Microsoft, so you can go to their website, deepspeed.ai. DeepSpeed is a deep learning optimization library. It's not a model, it's not a framework, it's a library that makes distributed training easier to run, more efficient and effective. And you'll see as we go through the material here that a lot of it is handles a lot of this management in the background. So it makes it a lot easier for you as a user to be able to take advantage of this optimization without having to do significant changes to your code and to your model. And so DeepSpeed is taking advantage of a lot of the things that we've been doing before. Again, we talked about data parallelism, model parallelism, memory management, managing parameters. There is an optimizer that does a lot of this. And this optimizer is called ZeRO. So we'll spend a good portion of our time talking about what ZeRO is and what it does for us in our models. When you look at the framework and look at the picture, you can imagine your model is here up on top. So this is the model that you're bringing to run. And traditionally, you would run that directly on your training framework like PyTorch. And then you'd run on an infrastructure underneath, and then directly on the hardware. In this case, you'd run this on Gaudi. DeepSpeed sits in between your model and the framework. So this is not necessarily a significant change to the architecture of your model. It's not changing PyTorch. It is simply optimizing how the data and information from your model is being presented into PyTorch and the infrastructure and the hardware. So again, think about DeepSpeed as simply an optimization library that helps manage the parameters, the training parameters, and your data. Okay, so let's talk about ZeRO. So the job of ZeRO is to reduce memory consumption. That's the primary focus of ZeRO, is to ensure that you can do more activations and more activity on your silicon and not be overrun by memory. Because again, we want to make sure that when you're training your model, all the parameters, your weights, your gradients, your optimizer states, your activations are all running on chip. And so if you have a huge model, it won't fit in your hardware. So what ZeRO is doing is basically reducing memory consumption by managing gradients and optimizer states across your available devices. One benefit of ZeRO is that from a configurations perspective, there's no model code changes needed. So once you initialize DeepSpeed, setting up ZeRO is basically all being done in the background. So as compared to some traditional model parallelism techniques that require some significant code changes to your code and your model, ZeRO in this case requires no code changes once you initialize DeepSpeed in your model. So a simple example of this is this picture on the right. So in a traditional use case here, this is sort of a traditional data parallelism use case, right? So you have the data split across multiple devices. But in this case, you look at this top blue box being your weights, this yellow box being your gradients, and then your optimizer states being these green boxes. If you were not managing these, you'd have to have these all running on every device. What ZeRO will do is allow these to be separated and run independently across multiple devices. So this uses a mix of all reduce and all gather techniques to run the information, share the information back with multiple nodes, and then be able to run. So now we're allowing much more efficient execution versus running the entire thing in each device. And then secondly, another technique that we'll take advantage of is activation checkpointing. So activation checkpointing can, again, further reduce memory usage by taking our activations, which is just our compute nodes throughout the model, and instead of storing them in memory, we'll execute them real time as we are doing a forward pass or backward pass. So instead of having the activations always available, we're executing them real time. So the benefit here is we're not storing these activations, saving our memory, but at a potential hit to performance and throughput because we are having to recalculate those activations every time. So let's talk about now the simple steps it takes to modify a model and have it be ready to run on DeepSpeed. So there are three key things here. So first is the installation of DeepSpeed itself. So at this time, Habana has its own fork of the DeepSpeed library. So we have our own version of DeepSpeed on our GitHub page. And so in this case, the user would install DeepSpeed here from GitHub. We have some optimizations in DeepSpeed that are customized to make Gaudi more performant. So in this case, we have our own fork of DeepSpeed. Then, as we said earlier, DeepSpeed is really handling the distribution of the workload. So in this case, previously you may used data parallelism, or in our case, distributed data parallelism for your PyTorch model. In this case, we're handing it off to DeepSpeed. So there are functions two functions, DeepSpeed initialize and another init function we'll see on the next page that hand off all that control to DeepSpeed. And this also then, DeepSpeed manages, again, the backward pass and optimizer. So your typical PyTorch functions here get modified. And all the details for this are here in the DeepSpeed website. So they have a very, very good getting started section that tells you how to manage these. But don't fear, we have, I'll show you some examples and some models that already do all of this. So all we have to do is basically just initiate a run. And that's what we'll do here in the next few minutes. Okay, so we talked about the initialization functions. So we talked about DeepSpeed initialize. Then also we have another function called DeepSpeed init distributed. And so the key thing here is setting the backend to the Habana communications library. So for those of you that are on NVIDIA, you may notice Nickel. So HICL is our version of that distributed library. So the key thing to do here is make sure that you are setting HICL as your distributed backend when you're sending this to DeepSpeed init distributed. And again, we talked about DeepSpeed initialize. So these are the two functions that are required to be added to your model to pass off all of the execution and handling to DeepSpeed. So now let's talk about the runtime. How do you actually initialize and execute a model? There are two files. So the one new file, or the most important file here, is the DeepSpeed config JSON file. And we'll show you these examples in just a moment. The dsconfig.json file is the file that sets all the configuration parameters for DeepSpeed execution. So this includes some of the hyperparameters, the optimizer that you're using, the zero state, so what level of zero optimization you want to use, and other DeepSpeed specific runtime variables. So the DeepSpeed website has a full set of APIs that define this. In most cases, you would start with the default values. And then the run command. So most DeepSpeed runs are run from a shell script, or you can simply use a run command that calls DeepSpeed, points to the DeepSpeed config JSON file, and any other runtime parameters. And the most important part for us is using the use HPU option. This ensures that we are running on Gaudi HPU. So we remember that in all of our models, HPU stands for Habana Processing Unit. So this is the nomenclature that we use to identify Habana products like Gaudi. Okay, so where can I, you're asking yourself, where can I get started? There are multiple working examples where you can run DeepSpeed models, which include a very nice and simple PyTorch example on our model references GitHub. This tutorial, we also have a BERT 1.5 and 5 billion parameter model on our model references, and also Hugging Face. So Hugging Face uses their Optimum library to run on Habana and has multiple models that have been fully optimized for DeepSpeed. So there are multiple examples here where these are just simply open up and run. Okay. So let's look at one of the important parts here is to know how much memory is being consumed in your model. And we've included some specific functions in our API to detect this maximum memory usage. And so we have these three: max memory allocated, memory allocated, and reset stats. You'll see this incorporated in our model here in just a moment. And so in this model, we've added a function called see memory usage. And this does make those calls to, with some simple math here, to detect and report out how much memory is being used during your model run. And so this gives you a feel for how much memory is being consumed by my model. We have a flag here called dump memory that we can add in the command line in our DeepSpeed run command to instantiate this and see the output. All right, so let's look at a model. We have a model that we found in the public domain called MinGPT. And we like this model because it's a very, very simple model. It's about 300 lines of code. And it's basically taking a very simple data set of numbers and sorting them and predicting a sequence. So it's taking the GPT architecture, using it as a transformer-based model, but it's very, very simple. So we have basically three simple files that we'll look at today and show you how to run and manage DeepSpeed using this very simple model. All right, so are you ready? Let's go. So our DeepSpeed model, we know, again, we've talked about the commands. So let's start looking at some of those commands. So first is our run deepspeed.sh. And all this is doing is simply calling DeepSpeed. It's pointing to our run script. It is pointing to the config file, and it is using HPU. So let's just get that up and running right now. And we're going to let that run in the background. I would like to then also, let's look at the actual dsconfig JSON file. So this is a standard boilerplate config JSON file that is defined by DeepSpeed. But a couple key things to note on this very basic starter file is, again, the optimizer that DeepSpeed is using. So in this case, using the Atom optimizer, using some of the hyperparameters, and more specifically, in this case, our ZeRO optimization. Now, in this case, we're calling this out as stage 0. And so in this case, ZeRO is not doing any management of our gradients or optimizer states. So we're not getting the full advantage of ZeRO and DeepSpeed managing that data for us. So the model that we're running here may or may not fit. So we'll see that in just a moment. All right, so let's start taking a look at the model itself. So as we said, the model here is about 300 lines of code. And we're not going to go through this in detail, but again, we remember that this is basically a GPT-2 based, transformer-based model that takes in a very simple line of numbers, sorts them, and predicts the next value. The trainer itself is a simple training loop that sets our training function and sets our data sets. But there's a couple key things I'd like to point out in this model. First is the import of our Habana frameworks. So again, for those of you that have attended our previous Getting Started tutorials, we've spent a time talking about incorporating the Habana frameworks PyTorch as well as the Habana PyTorch APIs. So these two lines are critically important, obviously, for incorporating Habana PyTorch and our APIs in the model. Now, we look a little bit lower here. We have this function called C memory usage. So this is a great example of how we are using those APIs. So this is where we have the memory allocated and the max memory allocated. So this is showing us how to actually use those APIs to track our memory run. All right. Now I just noticed something. It looks like our model has crashed. So let's take a look and see what happened here. I see it right here. So we see here memory allocation failed. So in this case, there is not enough memory to be able to run this model. So what are we going to do? Well, instead of using a DeepSpeed config without using the ZeRO optimization techniques, let's use another version where we now will turn on ZeRO optimization. And so now we're using stage 1, which is going to manage our optimizer states, and we'll also run activation checkpointing. So in this case, you will see here, when we turn on these things like ZeRO optimization or activation checkpointing, you'll see some default values here that we can set to be either true or false. In this case, we are using activation checkpointing, but these default values are set to false because we don't support them right now. But the activation checkpointing itself is up and running. And in this case, we will turn on ZeRO optimization. So our optimizer states will be distributed and managed across the workload. So now, instead of, let's go back here. Instead of running the simple one, we will run ZeRO1 underscore AC.sh. Now, in this case, same model, but now we will be running this using the DeepSpeed ZeRO optimization techniques. One thing to remember here is we are running across all 8. We're running on 8 Gaudis, and you'll see we're using the HCL backend. So this is 8 cards with HCL. And we will let this continue to run. So let's go back and take a look at our demo script. So starting with some of the models being parsed, I want to go to line 70. And let's look at some of the DeepSpeed initialization functions. So first here is where we're calling our DeepSpeed init distributed. And we set our distributed backend to HCL, just like we talked about in the slides. So, and again, we are setting use HPU in our runtime, as you saw here. So this is pointing us to running DeepSpeed init distributed with the HCL backend. Then we look down on line 149. In this case, this is defining the model type. So the one fun part about this GPT model is you have the ability to set these specific model types. In this case, we're using GPT-2 XL, which is fairly equivalent to a GPT-3 style size of model. well, actually a little bit smaller than that, but a significant model size. As you saw, it did fail before, and now we see that it is now executing and running. So as you have access to this, you can come in here and change this to larger models or smaller models to see the effect of what's passing and what's failing. Okay, we look down here on line 166, and you'll see our DeepSpeed initialize. So in this case, this is the function. Now we're handing the model to DeepSpeed. So we're taking all of our arguments, the models, our model parameters, and our training data, and passing them all into the DeepSpeed engine. And then finally, here on line 171, our traditional requirement for migrating models to Gaudi is setting our device to HPU. And this ensures that all of the ops that are coming down into our compiler are being run on Gaudi hardware. Okay, so let's take a look now at the output. One other thing I want to show you here is that as this is running, we can always run our HLSMI. And this HLSMI command shows us the capacity of all of our devices. And what you'll notice here is that all 8 of our Gaudis are using full memory. They're fully utilized in this case, and they're all running the Python script to run the model. So we see all 8 cards being fully active here. And as I said, this model is doing a very simple, taking a simple input of numbers and sorting them and doing some prediction. We cut this short here for the purpose of showing this example today. So the model is just about finished. Okay. So in summary for this, we remember that we have our run script, which is calling our dsconfig.json, setting HPU. We have our JSON file itself, which again is a default structure coming from DeepSpeed. In this case, we've set our ZeRO optimization, stage 1. We set activation checkpointing, and we execute our model. We also reviewed that we have the DeepSpeed initialize. And up here on top, we have the DeepSpeed init distributed to set the distribution and scaling, and our model type. So let's take a look back at the benefit of these techniques and what they can do for system memory. So in this case, the model that we just ran, which is a GPT-2 style model, you'll see this is not the GPT-2 XL that we just crashed. When we make it a model a little bit smaller, we can run that baseline, and we see 2.7 gigabytes. But when you activate ZeRO, we see this go down to 1 gigabyte. When you use activation checkpointing, this becomes even more aggressive and goes down to 758 megabytes. And then, of course, with ZeRO2, where we're doing some additional gradients and optimizer states, we have reduction from a gig to under a gig. We also see this effective in a real-world model. So if you want to go to our model repository, you can run our BERT 1.5 billion parameter model. And we have to use a ZeRO1 optimizer in this case, because if we don't, the model won't fit. So we see 18 gigabytes required being used here. And again, Gaudi 1 has a memory capacity of 32, so this fits just fine. But for even more aggressive memory management, ZeRO2 takes us down to 16 gigabytes. So final question, where can I do this? So we have two main places. One is on Amazon. So we have the DL1 instance. So you can go to Amazon and rent an instance and get access to Gaudi, access to 8 or more Gaudis, and run this demo or our examples from our website. If you're interested in running on our latest hardware, Gaudi 2, we have access to our developer cloud. So you can go to the Intel developer cloud and get direct access on the latest hardware, where you now have significant improvements in performance. And for example, we go from 32 gigabytes of high bandwidth memory on Gaudi to 96 gigabytes of memory. So we can now, even with using these techniques we've talked about in the last 45 minutes, run even bigger models and have ability to even scale even larger. All right, so now that we have a moment, I do want to make sure that everyone is familiar with the location of some of our content. So we talked quite a bit about the basic setup for DeepSpeed. And so for the next level of detail, you can go here to DeepSpeed Getting Started. And that talks you through all the things we talked about here in terms of DeepSpeed Initialize and some of those other things. This tutorial, this model is now loaded on our tutorials. So you can go to our tutorials site on our GitHub page and get access to this and do everything we did today, you can do yourself. And the instructions here are very straightforward and very easy to execute. And you can run these yourself. Our DeepSpeed BERT model is available here on our model references page. And again, fully documented instructions on how to go and run each of these models. And finally, from a Habana perspective, we have our DeepSpeed collateral. In this case, a very, very simple model here getting started. So we have a very simple model here that you can run and follow these steps and just simply see the model execute. And then for those of you that really want to explore further, you can go to Hugging Face, and Hugging Face has their own library optimized for Habana and an additional set of models and workloads that are supported with DeepSpeed. So the key thing here is start on our website and go right here and get started here. Okay. Okay, so that concludes the presentation part. Let's take a look here and make sure that our model did exit successfully, and it has. So we see all 8 nodes reporting that it has successfully completed the run. And again, we remember that when we did not have the ZeRO optimizer running, this model crashed. When we did turn on the ZeRO optimizer, it's now passing. So let's take a moment now to allow people to post questions. So we'll have a few minutes here for people to go into the Q&A and post questions. Okay, so for those of you, you can go into the Q&A and post questions. So Abdelrazik is asking a question around hands-on capability. So right now, Abdelrazik, as I showed you, this content is available here. So I'm going to put this in the chat. Alex, thank you for joining. It was good to see you at reInvent. Okay, so Bob is asking a question. The ZeRO optimizer is nice. How does it differentiate HBM on Gaudi 2 versus DRAM, or does it matter? Leon, you want to take this one?
Yeah. The ZeRO optimizer, it shouldn't matter for that, as it handles the partitioning of the model itself and communication of it. So it will handle it on the device memory, which Gaudi 2, I believe, is a lot more than the Gaudi 1 32 gigabytes.
Okay. Since we have a minute, I'm going to do one extra bonus here. So we talked about this previously. Let's do a run. We're not going to do this one. I'm going to add the dump memory flag here to the run so that as we're looking for questions, you can see what is happening. We'll see the output of the memory dump. So this is something, again, that a user would do not every time, but as they're looking at understanding where the model is building up memory. When we've done this, we basically see the maximum memory happening at the end of a forward pass once the loss function and gradients have been calculated. We see that being the place where the max memory limits are reached. And it did not like that because for some reason something got added on to the end of that. Let's check that again. Excuse me. Okay, so there we go. We'll let this run for a few more minutes. So we'll take a few more moments if anyone has any questions. Otherwise, if we don't see any more questions in the next few minutes, we'll end the presentation. We'll have, there's a survey. So if those of you we'd love to hear your feedback on the survey at the end. And also, I will mention that for those that would continue to, if you want to interact with us more, please go to our forum. So we have our developer forum. So you can come in here and push a question into training with PyTorch, and you'll see an answer, and you'll talk directly with us. So please, especially after we're done, if there's more questions or things that come up, please come in here to the forum and post a question. And now you'll see in this case, the API is starting to generate information here. So you'll see in this step before the forward pass, you'll see 2.8 gigs. And you'll see as it goes through each of these steps, after the forward pass, before the backward pass, after the backward pass, before steps. So you'll start to see this information starting to be generated. And so again, once the run is done, you can parse this information and see your maximum memory and where that is happening in the flow, either, again, forward pass, loss function, or backward pass. Okay, so I'm not seeing any additional questions. So again, your feedback is welcome. So please fill out the survey at the end. And we thank you for your time. Have a great winter break. And thank you for your time.